Okay. Welcome to the second lecture on the blockchain technology. In the previous lecture, we have seen the definition of the blockchain, as well as we have seen the difference between the centralized as well as decentralized system. Okay. So in today's lecture, we are going to discuss about the history, and the history related to the blockchain has been started actually in the 1991. Okay, where the three scientists Bayer, Harber and Stornetta, they use the concept of digital stamping related to the document. Okay, so if I just consider that I am available with the 10 lines of a word copy, and I am available with the 10 lines written on the paper, and if I make any changes to the soft copy, so it is very difficult to find out the changes, because after changing I have to after changing I have done the saving also, so I am not able that particular user has been changed the copy. But if I just go for the hardware thing, I am having the 10 lines written on the paper, and if I want to make any kind of a changes, so at that time I have to scratch the first word, or the word which is wrong one, or the word that I have to change, and again write down the new word. So it is very easy to find out the document has been changed. Okay, same is not the case for the soft copy. So in the soft copy, if I have done any kind of a changes, so I am not able to find out the previous version actually, or whatever the changes that has been done, I am not able to find out. Okay, so in order to avoid such kind of a thing, okay, the concept of timestamp a digital document has been introduced by the Harber and Stornetta in 1991. So what they have used, so they have done or they have just applying the hashing algorithm on the document. Okay, so suppose I am the user one, so I have created the file. So as the file has been created, its sequence number will be kept as a 0. Okay, and then let's suppose I have created the file, so I am just using my client ID over there, and when the file ID has been created, I have or I just added the timestamp over there, and at 0, that is nothing but the hash function. So the combination of all these four things has been done by the Harber and Stornetta. What they have done, so they actually just put as original document, so h0 will be kept as a 0 in this case. Okay, or the 0 value put over there once the document has been created. So as first time the document has been created, so the sequence number is nothing but the 0. The document has been created by the client ID C1. Okay, and when the document has been created, so the timestamp as well as the h0. So here h0 will be the 0th bit, because the first time it has been created. And now see, by using all these four parameters, that is the sequence number, client ID, timestamp and h0, the Harber and Stornetta applies the hash function on them. Okay, so what is the beauty of a hash function? So hash function have, okay, we'll discuss this hash function later on, but a hash function have the fixed bit output. Okay, it's having the fixed bit output. Okay, as well as they are having one more effect, that is what the avalanche effect. So for example, if I do any kind of a changes or little changes over here, so that may result into the large change in output. Okay, so input के अंदर अगर थोड़ा बहुत change हो गया, so that deals with what large change into the output. Okay, so what happens, see, let's suppose the client one have created the document. Okay, another client open that document and just make any kind of a changes. Here again we are not able to find out the changes, but we are able to find out who actually done the changes. Okay, so again one, as the changes are there inside of a document, so I am considering the document sequence number is nothing but the one changes has been made by the client C2 when the changes has been made, and here I must have to use the previous hash. Okay, because as it is the second change inside of a, as it is the first change inside of a document, so I am available with the h1, that is nothing but the previous hash. okay, or there may be chances another user comes, another user open the document, okay, so that's why the sequence number is next to the previous sequence number, client ID is the different one, then timestamp is again the third value, okay, and here I have to use the previous hash. So simply if I just consider this as a single block, okay, single block, single block, single block, okay, so I am having one block is connected to the another block by mean of a hashing itself, by mean of a hashing. So simply this is nothing but the timestamp digital document, which will indicate that how many users are there who actually changes the document, okay, when they have changed the document. And in order to make it trustworthiness, they have used what, the hashing function, okay, as the document has been changed for multiple times, so this will indicate how many times the document has been changed, okay. So after that, the Bayer, Harber and Stornetta used the concept of a Merkle tree in the 1992 to improve the efficiency by combining the time stamping of several documents into the single block, okay. So now this is related to the only one document, okay, this is related to only one document. So I can have a multiple document like what, doc 1, doc 2, doc 3, doc 4 and doc 3 and doc 4. So they have just done the combination of this one, okay, they have used the concept of a Merkle tree, okay, and use the concept of a time stamping for the several document into one block. So for that purpose they use the Merkle root actually. So in next slide we will discuss what actually the Merkle root. Again this same mechanism has been used inside of a Bitcoin in the 2019, okay. Now if I just consider the Merkle tree, which is developed by the Ralph Merkle in 1970, which is also known as an hash tree, okay. Again it uses the hash function basically. So in the Merkle tree, every leaf node is labeled with the hash of a data block, and every non-leaf node is labeled with the cryptographic hash of a label of its child node, okay. Now again just focus on this statement, every leaf node, okay, leaf node, so these are nothing but the last one, okay. So this particular if I just consider this as an Merkle tree, so this particular row is nothing but the leaf node. So every leaf node is labeled with the hash of a data block. So this consists of a hash, and which is basically on the original data available with me, which is basically on the original data available with me, okay. So now again consider that I am having 4 data available with me, D1, D2, D3 as well as D4. So on the D1, D2, D3, D3 and D4 I am applying the hash function. So every leaf node is labeled with the hash of a data block available with me, and every non-leaf node is labeled with the cryptographic hash of a label of its child node, okay. So whatever the intermediate nodes are there, or we can say the non-leaf nodes are there, so these are nothing but the intermediate node. So this non-leaf node is labeled with the cryptographic hash of labels of its child. So they were having the hash of, okay, they were having the hash of their child itself, okay. So likewise I must have to go to the root, and root is also consisting of what, the hash of its two childs, the hash of its two childs. So simply what is there in the Merkle tree, in the Merkle tree I am having the original data, let's suppose D1 is there, okay. So on that data I am applying the hash function. So this will give me a result. So that hash result will be let's suppose 1 2 a 4. So this is nothing but the result of applying a hash function on the document D1, okay. So I am having H00 available with me now. Similarly for the data 2 I am having H01. Similarly for the data 3 I am having H10. Similarly for the data 4 I am having H11, okay. So now I have to combine just two nodes with each other, by the meaning of their hash itself. Okay, so I can just create the intermediate node. So here H00 will be H00 will be combined with the H01. Okay, and I just obtain the new hash, that is nothing but a H of 0. Okay, and here also H1 is equal to H10 plus H11. So these are nothing but the previous hash added together. So I am having the new hash available with me. And here H root is equal to hash of H0 plus H1, hash of H0 plus H1. Okay, so here the root hash is available with me. Now this root hash, just having the information of all these 4, data 1, data 2, data 3 as well as the data 4, but can be represented by only a single string available with me. That depends on what kind of algorithm that I am using for the hashing. Okay, many of the algorithms are there for the hashing, like EMD5 as well as the SHA. So we'll discuss about that also later in the classes. Okay, so this is all about the timestamping a digital document which has been used in the 1991 actually. And again this Bayer, Harber and Stornetta, they use the concept of a Merkle tree for improving the efficiency by combining the multiple document together. And again they have used the concept of a digital timestamping. Okay. So they have created the block. The blocks are connected by using the hashes available with them. Okay. So this is all about the timestamp digital document as well as the Merkle tree. Now we'll discuss about the hash function, because in timestamping they also use the hash function as well as in the Merkle tree. Again the use of a hash function is same. Okay. So what actually the hash function? So this hash function map any size data to the fixed size. So for example, h of x is given to you. So I am just calculating x mod n, where x and n are nothing but the integer and mod is nothing but the modular operation. So x can be any arbitrary length, but h of x is in the range of 0 to n minus 1. That is what which is most important thing. So here your x can be any arbitrary length, okay, any arbitrary length, but h of x is in the range that is specified inside of a algorithm. So what actually the hash function will do, it will map any size data to the fixed size. Okay, now if I just consider, see, basically this hashing again it is used in the cryptography. What we are doing in the cryptography is nothing but the technique where you are converting the plain text, into ciphertext. Okay, so ciphertext, and again this ciphertext will be converted to the plain text in order to get the original message. Okay. Now consider that if I am just using a simple algorithm, that is what the replacement algorithm, like if I am having the input string as an A, B, C. Okay, so this can be represented as an B, C, D. So इसका मतलब क्या हुआ? So I have just shifted the position of my original string by 1. So ABC, if I just do the right shift, so I will get what? The BCD. So this is what my plain text, and this is nothing but the ciphertext. Likewise, I can have the hash function. Okay, here what will happen? It map any size data to the fixed size. Okay, and it can be represented like this: h of x is equal to hash of a given string, given number is equal to x mod n, x mod n. Okay, so here the output of h of x having the limited size. For example, now consider that x may be any kind of a value. Okay, x may be any kind of a value that will be put. So it may be a string, it may be a number, it may whatever it may be. Okay, here we are just considering it as an integer. Okay, and if I want to divide that integer in the two buckets, actually either 0 or 1. Okay, either 0 or 1. Okay. Now see, if I'm just considering x is equal to 10 and n is equal to 2, x mod 10 mod 2, it becomes what? 0. So this will goes to the this particular bucket. This number will go, this 10 data will be goes to the 0th number bucket. Okay, if I am having the input as an 7 mod 2, so this will goes to what? This bucket. Now again see, I am having number 510 mod 2, so this will goes to what? This particular bucket. Okay. So now if I just see this thing 7 10 5 510, okay, so these are a very large number and they are having what? Fixed size output, either it may be a 0 or it may be a 1. Okay, so here in h of x is equal to x mod n, x is called as a message. Okay, x is called as a message, while h of x is called as a message digest, where h of x is called as a message digest. Okay, so why actually all these cryptographically hash functions are secure one? Because they are the one-way function. They are the one-way function. That indicates if I am available with the x, okay, given x, we can compute h of x. But if the h of x is given, I am not able to apply any deterministic algorithm to find out the value for the x. I can only just guess. No proper algorithm is there which is responsible for calculating the value of x if h of x is given to me. Now consider again the previous example. If the h of x is given to you, h of x is given to you as an a 0. Okay, so you are not able to find out the value. That value is nothing but either a 10 or this is the 510, or you cannot guess. Like if I just apply this one 2 mod 2, it is also a 0 1. Okay, 2 mod 2, 4 mod 2, 6 mod 2. So we are not able to find out, or we are not able to calculate the value of a x if h of x is given to you. So that's why these hash functions are the one-way function. These hash functions are the one-way function. And for two different x1 and the x2, h of x1 and h of x2 is also a different one. That is what the another property for the hash function. So if I am having the two different strings, so their hash values are also a different one. And as well as one more property of a hash function is nothing but the avalanche effect. So this avalanche effect indicates what? A small changes in the data result in the significant change inside of a output. Significant change inside of a output. So simply this hash can be written like this one. So for example, if I am having input as a fox, so here the input string having the value, okay, or having the text three characters are there. Okay, so if I just apply the cryptographic hash function, its output, now these are the outputs according to the ESHA1 algorithm. Okay, so which is 160 bit. So as per our definition, this is nothing but the message. Okay. This is nothing but the message, and this is nothing but the message digest. Right. So I am having the fox as an input. I just apply the cryptographic hash function. So here I am having the SHA1 which is 160 bit. So 160 bit. Now if I just consider this, these are the hexadecimal output. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 20 plus 20 40 40 into 4, it becomes a 160 bit. Okay, so because this is nothing but the hexadecimal number which can be represented by using a 4 bit. So 40 into 4, it becomes a 160. Now I am just having the another the statement as an input that is nothing but the red fox jumps over the blue dog. Now here in the previous case I am having only one word that consisting of 3 character. Here I am having 1 2 3 4 5 6 7 8 words, but the output is how many, or how much long the output is? So output is 160 bit long. Okay. So likewise here we can just say that x, that is what the input can be any arbitrary length, but h of x, that is nothing but the message address, is in the range of 0 to n minus 1, or the specific. So here the range or the output is of size 160. Output is of size 160 always, whatever the size of input. So the red fox jumps over the blue dog. Now this is what the digest for the same 0086 and so on. Now I have just made some changes over here. The red fox jumps instead of a v, I just written over as an u, and you can see the large difference inside of the output, and this is called as an what, avalanche effect. This is called as an what, avalanche effect. Okay, small change in the input result or varies the output in the larger change. Okay, again here the red fox jumps, instead of a u I have or o, the spelling of a or will be written as an what, o e v r, and again I have the different output. Okay, and again if I just miss the v over here, okay, miss the v over here, again I have the different output. So that is what the beauty. And if I just see this output, I am not able to find out the whatever the given input. So that's why the hash functions are nothing but the one-way function. Hash functions are nothing but the one-way function. So if you just consider the example over here, so I am having the SHA1 algorithm available with me, and here I am just writing the hello, okay, and applying for getting the hash. Okay, so this is hash for here hello, that is nothing but f7ff. Now if you just consider the length of the output, so length of output is always same, that is nothing but a 160. Even though if I just write down hello everyone, how are you, okay, and just calculating the cache. So the length of the output remains same. The length of a output remains same. Okay, now if I just make any small changes, instead of a u, okay, I have just used the WhatsApp kind of a writing, how are you, and now I am just calculating the hash. Just observe the difference. Okay. A small change in the input will make a large change inside of a output, and that is known as an what, avalanche effect. Okay, so we will stop here. In the next lecture we will discuss about the public ledger, actually what is there inside of a public ledger, how it can be used inside of a blockchain.